the angle in the equatorial plane, and theta is the latitude angle. Okay, and then you have these vectors E phi, E theta that are tangent vectors, and Ez that is the normal, the outward normal. The problem with this system is there is a breakdown at the North Pole. You can see this geometrically because at the North Pole, it's not very clear what east and west should be. Okay, so you need to use two charts. It's not a problem, it's just annoying. So you want to use, I mean, it's advantageous to use charts that are somewhat similar. So what you do, I mean, what this is saying is that you do two rotations. Always there is a problem. This is, I go back here, there is something called the date line. Okay, so let's say that longitude 0 is Greenwich on Earth, and this is 0 degrees latitude, and at 180, that's somewhere in the Pacific, you have the so-called date line where there is the passage between this day and the next one. Okay, so there is a problem there, and what you do is you rotate the system of coordinates, and you find, this is how it works to have, it's this transformation, x, y, z goes into minus x, z, y. So first you rotate about the x-axis and then about the z-axis. And you move the date line to this red thing along the new equator. So you can build two charts, and I can work in one chart and in the other things were similar. So what I want to do now, I want to write the Euler equations. Okay, so I need coordinates, and the coordinates are okay, the tangent space has these two vectors. Theta is latitude, the volume element is the sigma written here, and then I need gradient, divergence, and Laplace. Okay, but this is Laplace-Beltrami, is the Laplace operator on a sphere. It looks like this, where again tangent, I mean theta is the latitude. There will be a singularities at the poles because cosine of theta is 0. I cannot divide by it. So what this means is that these expressions are valid everywhere except at the two poles. If I want to deal with polar regions, I need to make these two rotations, and then there will be no problem. So I have to use another chart, but I will just work with one, and then it will be similar in the other. So what are the equations? Okay, so it is important that the Laplace-Beltrami, it operates on the completion of the smooth functions with mean 0, and this is the inner product. Okay, d sigma is the volume on the sphere, so it's not dx dz. There is d theta d phi, and there is a cosine of theta. This is the standard thing. So this is the inner product, and it will be important to find explicit solutions to look at the spectrum of this Laplace-Beltrami operator, and the spectrum is well known. It consists of discrete eigenvalues that are minus j plus 1. They are the so-called spherical harmonics, are an orthonormal basis of eigenfunctions, so they satisfy this. And the eigenspace Ej, j is greater or equal 1, has dimension 2j plus 1. Okay, and these spherical harmonics are I mean they are Pauline, I mean I will, there are explicit formulas for them. So now what are the equations that that govern this? Okay, the equations are here. First of all, there is another advantage of the stratosphere with respect to the troposphere, is that the flow is inviscid, so viscosity is very small. So I don't have to use Navier-Stokes, I can use Euler. So these are the Euler equations on a sphere. U is the velocity east-west, V is the velocity north-south, and it's written in spherical coordinates. This is why you see all these trigonometric functions with thetas in them. U0, V0 are velocities, P0 is the pressure, ρ0 is the density, omega is these terms. You see, u v0 tan theta minus 2 omega. These come from the terms with omega. Omega is the rotation speed. Okay, so this is the Coriolis contribution. And what will happen is that, so these functions depend on phi, theta, and the radius. So at every radius, I consider a flow, and the flow depends on the radius. It's like spheres on top of the spheres, and this is two-dimensional flow. So the first two equations are the Euler equations. Well, the third is, so these are Euler equations, the first three, and this is mass conservation, the fourth one. And there is no vertical flow in the stratosphere. Basically, the flow is in the tangential flow at every height. So I will not have, I will only have Z dependence in the, Z is the vertical, in the density, in all these velocities, but there is no variation. So this is why the third Euler equation has a 0, yes, here. So this is the one for the vertical. This is an easy expression. Now, here it's written using the third equation, actually using the fourth equation. Okay, the fourth equation, the mass conservation, tells you that there is a stream function. So there is a function psi, so that u0 is like the gradient. I mean, is minus the gradient. Well, is the orthogonal of the gradient. It's this thing here, like the stream function in planar geometry, but this is in spherical geometry, so is this cosine. So this is the fourth equation. And the advantage is that instead of having u and v, u0 and v0, now I have one function. So I don't have so many unknowns. There is a structural thing that I can use to simplify. And then I can write, eliminating the pressure between the first two gives the vorticity equation that looks like this. This is the Laplace operator here, this gradient square. Okay? Now, just as a comment, if the density were constant, this is inviscid flow on a rotating sphere. But here the density is not constant. It decreases with r, and so does the pressure. And there is a relation. This is the equation of state for the gas between temperature, pressure, and density. Okay, but if I know, so what I will do, I want to look for simple solutions, for the simplest possible. There are not many explicit ones available, unfortunately. So here is an important observation. I want to look for traveling wave solutions, and the Laplace here is Laplace-Beltrami, okay? Everything is in spherical geometry. So if I solve this elliptic, nonlinear elliptic equation, so if I find an f and a psi that satisfies Laplace of psi equal f of psi on the whole sphere, then I can change the psi 0 in this way. So what is the change from psi 0 to psi? There is a shift. This omega t is a shift in the phi is the longitude. Okay, this is the rotation effect. Rho0 is a scaling because of the density that changes with height, and omega sin theta is something that comes from Coriolis. So if I solve this, which is not time dependent, this elliptic problem, then I find a traveling wave solution of the system, of the physical system in the stratosphere with rotation. And here is the expression of the pressure. Okay, so any solution of this time will describe waves that depend on traveling waves that travel exactly at minus the rotation speed. So they travel in opposite to the rotation. And for those solutions, I find I can allow any density that depends just on z, and I find a solution. So this is a trick to reduce the degree of difficulty to try to solve an elliptic problem on a sphere, and from then there to find physical solutions. And these will be height-dependent stratospheric planetary flow that propagates zonally westwards. This traveling wave travels at speed minus omega. The orientation is in the direction of rotation, so they travel westwards. Okay, this is the ansatz. So I will look at this elliptic equation. Okay, this is the fact that the singularity is only, the singularity at the North Pole is not a problem. And you can, these are some considerations how you can write the equation in a material derivative form. And these are the covariant derivatives and the complex structure. So basically what I'm looking for is for the stream function psi. And if I have the stream function, okay, then the velocity field is related to omega is the vorticity, big omega. And this is how from the vorticity I find the stream function. So there is a law called Biot-Savart law. This is the green function. And I have a constraint here that has to be 0. This is the so-called Gauss constraint. So if I have a stream function with vorticity satisfying this integral constraint, I can find the flow. Okay, in terms of Hamiltonian systems, the problem, there is a symplectic structure. This is the Poisson bracket, and the vorticity equation can be written as a Hamiltonian system in this form. Now, the first question is existence and blow-up. And in two-dimensional Euler flow, there is a Biele-Kato-Maeda global existence result in 2 dimensions that generalizes to this setting. So it's similar. So this means that if I start with the smooth solution, there is no blow-up. It will continue to exist. So the interesting question is what happens to this solution. Now, looking for solutions, one important aspect that is often used is symmetries. If there are symmetries, this helps to reduce the dimension. What kind of symmetries are here? Well, I would like to remove the problem to a fixed sphere, but of course I have to pay a price because these planets rotate. So basically, if from psi 0 is the stream function, I pass to psi omega, which is this expression, non-trivial with the time dependence and this extra term here on top, omega sinus of theta. Psi 0 on a fixed sphere corresponds to psi omega on a rotating sphere. Okay, this is one thing. Then there is a scaling invariance, and there is another invariance related to the symmetries of the sphere. This is the orthogonal group, and this is how you can obtain them. So what I'm looking now is for conservation laws. There is a correspondence between conservation laws and symmetries. So what are the known conservation laws? Well, the first one is kinetic energy, which takes this form. Then big omega is the vorticity of the flow. This is conserved, it's called the Casimir, because for every big F, this integral is conserved. And then there are the first eigenspace of the Laplace-Beltrami operator. This also gives me some conservation laws. These are the conservation laws that are available. Okay, so now I look for stationary solutions, and basically what I have is all this discussion is to say, I want to solve this elliptic equation on a sphere. Omega is a positive number that corresponds to the rotation of the sphere. Laplace is Laplace-Beltrami, and f is any function that I want. So any solution of this corresponds to a solution on a rotating sphere. Okay, so how many solutions are there? Well, first of all, there are zonal solutions. So solutions that depend, zonal means that at every latitude, it depends only on latitude, okay? So at every latitude, the zonal solutions are these things that I showed in the beginning. The ones that you observe when you look on the top of the troposphere, you basically see flows that go east-west. So at every latitude, the flow has a certain speed, but it doesn't go north-south. These are solutions where the stream function depends only on theta, so its derivative with respect to phi, which would be the meridional speed, is 0. They are only east-west. And this is easily obtained because you obtain an ODE, okay? For this. There is only one variable, so it's an ODE. So there are zonal solutions that are explicit solutions. And then, when big F is a linear function, but not just any linear function, when big F is this specific linear function related to the spectrum of the Laplace operator, there are these explicit solutions. So what are these solutions? Well, first is some coefficient there. And you see J should not be 1 because I don't want to divide by 0. But for every J, every eigenspace, there is this term here that somehow adjusts to the fact that this is rotating. And then some linear factor times an eigenvector. Okay, and the eigenvector is called, the eigenvectors are these spherical harmonics, okay, or, I mean, they are known. It's polynomials that, so these waves are called Rossby-Hurwitz. And they have an interesting story. Rossby was a Swedish geophysicist that derived them in planar geometry, and then Hurwitz was an American physicist that generalized it on a sphere. So now they are called Rossby-Hurwitz waves. And these are solutions to the Euler equations written here for F linear. Okay. And right, so these are explicit solutions. So how do the so these are for a fixed sphere. For a rotating sphere, this is how they look like. So they are traveling waves. There are traveling waves, and there are waves that propagate at speed c. And then there are the speeds that are interesting is c and omega. And these are the formulas. Right, so now the first type of mathematical result that, so until now is just writing the equations and explaining from where they come from. So now I'm going to talk about some results that we have. There are in geometrical problems, there are some so-called rigidity results. So things that say that when you solve an equation like this, if the derivative of f is satisfies certain constraints, then only constants are possible. So for example, here, this is the elliptic equation that I want to solve. If f prime is positive, strictly positive, then only constant solutions are possible. You prove this by multiplying and deriving Poincare inequalities and things like this. So that f prime is positive, then psi is constant is not surprising. The surprising thing is that typically results of this type can be done for general Riemannian surfaces. And the condition that is used there, because these are some Poincare inequalities. So there are Poincaré inequalities, and then the derivative of f will come in there. And if it satisfies a certain inequality, then you only get trivial solutions or explicit or eigenspaces. So the typical thing is that f prime should be larger than the smallest eigenvalue. For the sphere, the smallest eigenvalue, different from 0, is -2. Well, here we have -6, which is the second, not the first one, it's the second. And this is, we can do this because we have a lot of symmetries here. So this is an interesting result, because what you expect is some comparison with the first eigenvalue, but here it works with the second. It is optimal because this Rossby-Horowitz wave is a solution for -6. And these are spherical harmonics that will not, that is any non-trivial combination will satisfy it. So you don't, -6 is the best that you can obtain for the sphere. So this is a so-called rigidity result. Right. So now, these tricks about, there are some other examples of explicit solutions, not many. This is an open problem. I mean, in principle, it should be possible to find others. We didn't find that many, but one possibility is this. This thing here is a non-zonal solution in the sense that it depends on theta and on phi for every fixed phi 0. Okay, so it's one solution, and this is a second solution. And they look very complicated. They are complicated, but it's because in deriving them, there is a trick, namely, what you do geometrically, these solutions are they describe a flow where everything flows on circles like this. Okay, so you fix a point, and then everything rotates around that point at a speed specified by this. Right, so now we have very few explicit solutions, zonal flows, and these Rossby-Horowitz waves. And then some special ones that I just showed. And I believe that this category can be extended. It would be interesting to find explicit flows. It's important to find explicit flows because an explicit flow permits you to compute various things and to understand what is going on. The other option would be to approximate. The problem is that when you approximate, first, the typical approximation is you take planar geometry, so you already lose things, then you throw away some nonlinear terms. And well, when you get to the linear level, basically you are quite far away from the physics, so it's very questionable whether what you can prove has any relevance to what is really observed. So it would be preferable to work in the nonlinear framework. And we have these explicit, so the zonal solutions. So the zonal solutions have this type of velocity. It just depends on theta. And here omega 0 is the vorticity. Okay. So the divergence, but it's divergence in spherical coordinates. And there is a nice trick due to Arnold to prove stability, or to try to prove stability. So the Arnold method consists of the following. You try to fabricate an expression, a functional that relies on these invariants, on conserved quantities. Okay? And then you hope that the first derivative, the first variation would be the Euler equations, and then the second variation should be positive. Then this gives you stability. Okay, this is, so here the first is the kinetic energy, this is this Casimir, and this is the thing, the other conservation law. So here I have the freedom to choose k and a. A is a constant, k is a function. Okay. So indeed, I can compute the second variation. And the interesting thing, so this is a refinement of Arnold's method. Okay. So if you look here, this is the result. So the idea is you take this functional, the first variation are the equations, the second variation is you can bound it away from 0, and then you get stability. To be able to do this amounts to finding an epsilon and an a such that f prime is the velocity, g is the derivative of the vorticity. Okay? You need to satisfy this condition. So if this condition holds, then I can work with this functional and get. So this is an improvement of some more recent results about using this method of Arnold. Okay, how does this apply to anything useful? Let's just look at Uranus and Neptune. I'm looking at these because I will show you again the. Now, there is a result in these stability things for this kind of problems that if you have an inflection point, this is bad. So an inflection point is where the convexity changes. Unfortunately, all of them have inflection points. But if you look at Jupiter and Saturn, these oscillations, so these are zonal flows, are very, very strong. On Uranus and Neptune, they are milder. The velocities are very big, bigger than on Jupiter and Saturn, but the changes are less. So if there is a chance for these zonal flows to be stable, it would be on these two planets. And this is what I'm going to show, that this is indeed the case. How? Well, the flow on, this is this profile here, this U0 is a profile. Okay, it's a nonlinear, it's a velocity that depends on the latitude, and it's 0 at the two poles. And for suitable constant alpha, beta, and gamma, this mimics, this is a model for what happens in the stratosphere of Uranus and Neptune. If you compute this expression, okay, I need to show that this expression is bigger than epsilon. This applies if this has the same, if these two polynomials here in cosine squared have the same roots. And for Uranus, this is the second, for Neptune is this, and they are stable. Okay, so this slight improvement of Arnold's approach gives the stability on Uranus and Neptune. It doesn't work for Jupiter and Saturn. The profile there, it won't be a quadratic polynomial because there are too many oscillations and the condition is not satisfied. It seems, well, this just means that we don't know how to prove it because, well, experimental data in the sense of field data, observations. Observations seem to show that these flows are stable, these zonal flows are stable also on Jupiter and Saturn. But the problem is the time scale. You see, the observations that were done are, well, if you are really optimistic, a few hundred years if you count early observations that were not very reliable. So we have a very short time span when they didn't change a lot. So that could also be continuous dependence on data, because the time scale of 1 century is not enough to claim that it's stable, or 2 centuries. So it's not very clear whether they are stable or not stable for Jupiter and Saturn. So this is a so now there is, again, this is an another play out with this with this method of Arnold, if f prime is between 0 and -6, then the stationary solutions are stable. So I showed you one stationary solution that are these circular paths, and with this improvement of Arnold, one can show that that is also stable. Okay, so now there is one interesting question related to the Rossby-Hurwitz waves. So these were the explicit waves that were obtained by taking this big F to be a linear function and using the fact that we basically know everything that we want about the spherical harmonics, about the eigenvalues of the eigenfunctions of the Laplacian on the sphere. So there are, these waves are they have a notation, yes. So there is an interesting question. Degree 2, the question is the degree 2 wave, is it stable or not stable, the Rossby-Hurwitz wave? So this doesn't work with Arnold's method, and the numerical evidence, it's very complicated and it's conflicting. So there are recent papers that, this is a survey paper from 3 years ago, where they explained that different people reach different conclusions. Some said it's stable, some said it's not stable. Okay, so now we have a proof that this Rossby wave, this Rossby-Hurwitz wave, this one here. So these are unstable and these are stable. So the Y20, Y20, let me explain the notation. This is a spherical harmonics. Alpha sine theta is something that accounts for the rotation of the Earth. Beta is just a factor, and Y20 is the spherical harmonics of the eigenvalue -6, and the 0 on top means that it doesn't it's zonal. It doesn't depend on longitude. So there is an explicit formula for it. So this is a Rossby-Hurwitz wave, and first, the instability. So what's the difference? The difference is that here, if they have too many oscillations, they are unstable, and if they are zonal, this one is the zonal one, the one with 0 on top, that one will be stable. Now the instability is not too complicated. I will show you, I will briefly explain in the last 5 minutes, how do you prove stability for something like this, for this wave here, this Rossby-Hurwitz wave of degree 2. So this is a real wave. I mean, these waves are really observed. But like I said, field data is not reliable because first you have, these waves typically are superimposed with other waves, so it's very difficult to follow them. And well, there's also the issue of the time scale. So what do you do? Well, first of all, you use an invariant, and then basically you use the invariance, but there is a nice, the idea is the following. You take a stream function and you expand it in terms of the spherical harmonics. They are an orthonormal basis, so you find these coefficients here that unfortunately have many indices. And now you try to take advantage of the conservation laws, and you have a few to deduce something about these coefficients. And what you find by looking at the conservation laws, basically this is the interesting information, that the instability can be caused only by energy transfer between the spherical harmonics at level 2. So it's just some coefficients that you need to control. Yeah, so if you look at this, so basically what we can show using the conservation laws is this relation that is written on the bottom here. And it's important that L is 3, is greater than 3, because then this coefficient is positive. And if it's positive, this tells you that this sum remains small if it starts small, the sum of the coefficients. The factor in front becomes negative for L equal 2, where the problem is. For L equal 1, yes, and for L equal 1, you can sort it out with the conservation law. And then the way we can prove stability is we look at these conservation laws, 2, 3. So this is this Casimir. It's this vorticity modified, and this is invariant in time. So this gives you polynomials of degree 5. Well, of degree, yes, 2, 3, and 5. So you have expressions where there are all these coefficients that come in. They are nonlinear expressions, and basically you reduce the problem to a problem in algebra that a system, nonlinear system with 5 unknowns has to have solutions that are controlled, that are small, and we can prove that. So this is a survey of what we've been doing and why. So basically we have an Arnold type result for stability of zonal flows that unfortunately is applicable only for Rossby-Hurwitz waves of degree 1. So these are very simple, are sine of theta times the coefficient. And then we need, it's a much more complicated work to do this. For the next more complicated Rossby-Hurwitz wave of this type, which involves a spherical harmonics of order 2. And the interesting thing is that from order 3 on, they are unstable. So basically, the open question is the ones of degree 1, the degree measures how many times they oscillate. The ones of degree 1 are stable. This is by Arnold. The ones of degree 3 are unstable. This is the calculation here that is not very complicated. And what happens at degree 2? The zonal ones are stable. This is what we prove. The non-zonal ones, we don't know. And well, like I said, the field data is not reliable, so I don't know what the answer should be. This is more or less what I wanted to present.
So thank you very much, Professor Adrian. So as usual, we are going to pass for the questions or comments. So you are free to if anyone would like to make a question or to write in the chat. I can see here the chat. It seems that there is, well, well, first of all, I'd like to thank you very much for this wonderful talk. Yeah, so many, I mean, subjects, né?
Yes.
Based on manifolds, Euler equations, on spheres. So, and now you have present this Arnold method for stability, which seems very interesting. I'd like to know more about it. Yeah. So I could ask something. I mean, just to let me know, is the unstable flows you could not think, it would not be observable. Yeah. If you
yes. So the unstable ones will basically in time they will and they will change so much that they are not recognizable anymore.
Yeah, they are not be. I mean, they are not. They are going to stabilize and they are going to see it. I mean,
I don't think that they stabilize because they have a lot of, you know, they can. It's compact, but they have a lot of places to go. I mean, the stability here is stability in the strong sense. So Lyapunov.
Okay.
Starts small, remains small. There is also the possibility of orbital stability. Okay?
I see.
So orbital stability means that they travel at, they somehow, the form remains, but they move around. I'm not aware of any result of orbital stability, but, you know, in principle, typically what you expect is, so there is a gap here, there is stability for the low modes.
Yeah.
And so for 1, the zonal one for 2, and instability from order 3 onwards. So maybe at order 2, there, I mean, typically the transition between, there might be some orbital stability here at play, but we did not investigate it.
Let me ask you one more thing, curiosity. If
Yes.
Sorry if I lose something, but it seems to me that all equations are incompressible, all equations, yeah? You have the versions of
No, they are compressed. Well,
they are compressible.
Well, it depends. You see, they are incompressible in 2 dimensions and compressible in 3. So basically, but at level 2, yes, they are incompressible. Yes. So the density at every fixed height is constant. Okay. So the density changes with height, but I will go back to this. This is a very good point, actually.
Yeah.
Because let me look. Let me show you this form of the. Where is it?
Because of the Mach number should be
yes,
big
here.
than 0.3. Yeah.
So you see what happens here at a fixed Z, which means for a fixed sphere.
Okay.
This is a flow. This is incompressible. But then when you go up, the fact that rho is smaller makes this bigger. Okay, so there is scaling, so it's incompressible in 2 and compressible in 3. And in 3 dimension, the flows become simply bigger. You see, there is this factor here. The effect of the height is this factor in front that makes it bigger. Rho 0 becomes smaller as you go up, so this becomes bigger. The more you go up, the faster they become. I mean, but the analysis, the 2-dimensional analysis is incompressible, yes.
Yeah, so this is why you have used this Kaito.
Yes, exactly, yes, yeah.
Yes. So, well, I'm not going to ask all the questions. Maybe someone would like to I could not see. So, you could see some questions in the chat. I couldn't.
Not question.
No questions, yeah. So let's thank you again, Professor Adrian Constantin, for this beautiful talk, and I appreciate so much.
Thank you very much for the invitation. Thank you.
Okay. Thank you, Vladimir, and thank you a lot, Professor Adrian Constantin, for your amazing talk.
Thank you.